Generally speaking, most people do not think of themselves as physicists. In reality, however, the average person has an intuitive sense of physics without fully understanding why. For example, what do you think would happen here? I imagine most of you could have guessed that this would happen. However, some of you might not know why this happens. So in today's video, we will explain the physics behind reactions just like this and concepts such as momentum and impulse. The collision between the yoga balls that we just observed could be best explained by the law of conservation of momentum. However, in order to truly understand what that is, we have to first understand what momentum is. For any given system, we define the momentum as the mass of that system times the velocity of that system. Using this new definition of momentum, we can finally define the net initial momentum of the collision between the two yoga balls. As seen here, the initial momentum of mass 1, which is circled in blue, containing me and the yoga ball, is equal to that mass times the initial velocity 1. Whereas in mass 2, the initial momentum is equal to mass 2 times the initial velocity 2. Therefore, we can define the combined initial momentum, also known as net momentum, as m1 times v1 initial plus m2 v2 initial. Now that we have a firm grasp on the concept of momentum, we can look to define the law of conservation of momentum. This law simply states that in a collision or reaction between two or more objects, the net initial momentum will be equal to the net final momentum. So, we can explain the elastic collision between the yoga balls, given this law of conservation of momentum, by stating that the net initial momentum of the yoga balls going towards each other must equal the net final momentums of each of the yoga balls going away from each other in the conclusion of the collision. This information is cool and all, but the only way to quantitatively support the law of conservation of momentum is to head to lab.
My name is David House. Welcome to the Momentum Lab.
In this lab, we will observe 4 different types of collisions between cars in order to see the law of conservation of momentum being applied. First type of collision we will observe is an elastic collision. In this collision, the magnets on the carts repel each other and propel the carts in opposite directions. The second type of collision we will see is a perfectly inelastic collision. In this collision, the Velcro of the two carts connects at the end such that their final velocities are always the same. The third type of collision is an inelastic collision. This is like the middle between an elastic and totally inelastic collision, as the carts bounce off each other slightly, but not to the extent of an elastic collision. The fourth and final type of collision is an explosion. This is pretty self-explanatory, but to put it in layman's terms, the main characteristic of an explosion is a very, very sudden change in momentum. When linearizing the data of these collisions, we want to keep in mind the law of conservation of momentum. According to this, the net initial momentum and the net final momentum should have a 1-to-1 ratio. Therefore, if we were to set up a linear relation between these two quantities, we should get a slope of 1. As seen in our graph, the slope is almost exactly 1 with less than 1% error. So, it's pretty safe to say that our lab supports the law of conservation of momentum. The second important concept for this presentation is impulse. Impulse is simply defined as the change in momentum in an object. Additionally, there is a second way to represent impulse. As we know, when you change the momentum of an object, you exert a force onto that object, which would then change the acceleration. Therefore, the equation for average acceleration, which is equal to the change in velocity over the change in time, is very relevant to this. Additionally, we know that this same acceleration is equal to the net force over the mass given Newton's second law. If we then set these two equations equal to each other, we get the change in velocity over the change in time is equal to the net force over the mass. If we then multiply both sides by the mass and both sides by the change in time, we can get that the mass times final velocity minus the mass times initial velocity is equal to the net force times the change in time. As we know, the this left side of the equation, mass times final velocity minus mass times initial velocity, is equal to the change in momentum. Therefore, we can establish that the net force times the change in time is equal to impulse. One very easy way to see impulse in the world around us is through the game pool. As seen in this example, the 5-ball very clearly experiences a change in momentum due to the force that the cue ball exerts onto it. Therefore, according to our definition, the impulse of the 5-ball should be equal to the force that this cue ball exerts multiplied by the contact time of the two balls. While on the topic of impulse, one theorem that it's absolutely crucial we hit is the impulse momentum theorem. This theorem essentially combines the definitions of impulse and momentum and puts them into one concise equation. This equation states that the sum of all the masses in a system times their initial velocities plus the net force times the change in time is equal to the sum of all the masses in a system times their final velocities. In the context of the collision of the pool balls, as we were talking about earlier, the impulse momentum theorem would tell us that the mass of the 5-ball times its initial velocity plus the force due to the cue ball on the 5-ball times the time in which they are in contact should be equal to the mass of the 5-ball times its final velocity. Despite this example, we still need quantitative evidence that the impulse momentum theorem really holds up. In order to test this theorem, we will run a car into a force probe and measure the impulse that this probe exerts onto the cart, as well as the final and initial momentum, and combine these into a linear relationship. There are numerous ways that you could linearize this. However, what we decided to do was take the initial impulse momentum theorem and just slightly modify it such that the impulse is equal to the change in momentum. And as we know, this is the definition of impulse, and therefore there should be a 1-to-1 ratio and a slope of 1 in this linear relationship. As you can see from our graph, we attained a value of 1.26, so we had roughly 26% error. And although this value is not great by any means, we still believe that the impulse momentum theorem holds true, because as you can see by this new graph, we attained a slope value of 1.09 by only taking out our two biggest outliers. So we believe that the majority of our error was due to random error, because this is the week before exam week, so tests, projects, quizzes are stacking up, and students are extremely stressed during this time, and we believe some of that stress may have made its way into our data keeping and led to the error. So we, in conclusion, believe that our data still supports the impulse momentum theorem. And with that, I'll send you to Nathaniel for one last important message.
Thank you for watching.